The screen is yours.
Thanks. So thank you all very much for surviving the first 8 talks, and I hope that you will survive the last one as well. So first, I would like to clarify an issue about the organizers of this summer school. So Galit and Janos, they thank the organizers, but who are those organizers? So I don't think the webpage says anything about it. So actually, this is a joint teamwork of Miklos and all the speakers, including Janos and Galit, who thanks themselves. So everyone did his part in the organization, and this summer school came up to be. So thank you very much, everyone. And for me, all this started, and actually this summer school as well, I think it started in just before the COVID started in January or December 2020 it was, or many years ago before the COVID, when Janos visited Tel Aviv and suggested to work on games with general payoff functions, that is Borel games. And I thought I work usually with payoff functions, which are the limit of the averages. Those games are difficult. So I thought that with general payoff functions, nothing can be said. But okay, I mean, Janos, you know him, he's very sweet, so why not work on what he suggests? And then the COVID came into our life. We had plenty of time, and this very difficult, seemingly very difficult topic, I mean, we had time to crack some problems. You've seen the presentations of Galit and Janos this morning, some results that we could have done. And now those two results are new papers. So the paper that Janos presented with countably many players was just submitted. The paper with the first paper on regularity and its implications was not yet even submitted. So everything is really fresh from the oven. And this result that I will present now is also very, very new. So what we've seen so far is essentially today, we've seen games, repeated games with tail measurable payoffs, and bounded and Borel measurable. But the main property that we needed was that payoffs are tail measurable. So Galit presented repeated games with finitely many players, finitely many actions, and we proved that for every epsilon there is an epsilon equilibrium, together with a fault theorem. And Janos showed us how to extend this result to countably many players. We also saw the example by Wurenfeld about a counterexample, a game with countably many players without epsilon equilibria, since the payoffs are not tail measurable. And a very basic open problem is what happens when the number of players is finite, but the payoff functions are not tail measurable. So drop the assumption of tail measurability and then ask whether an epsilon equilibrium exists. So this is an open problem. And even if the payoff function is the limit of the average payoffs, the long run average payoff, even then, when there are at least 4 players, or even at least, and even 3 players, and even 2 players, we do not know whether an epsilon equilibrium exists. But when the limits are, when the payoffs are the limit, are the long run average payoffs, for 4 players, it is an open problem whether there is an equilibrium, an epsilon equilibrium. So in very simple games. So essentially, this is an open problem, and therefore it's not. It is difficult. So it's not clear whether we can do anything yet about it. But as we've seen in the first two talks today, then something can be said. But I will try to weaken the assumption of tail measurability. And today I will show you one class of games without tail measurable payoffs where we know that an epsilon equilibrium exists.
I have a question.
Yes.
I have not been able to listen to all the talks, but I'm a bit surprised by this notion of countably many players. Is there any game theory where one considers uncountably many players?
Yes. So there are games with a continuum of players. If you think about markets with continuum of consumers, then you can, or with many consumers, then sometimes you model it by continuum of players. There are models of matching when you have continuum of players who you match to each other. So there are various models with continuum of players.
But it's rather countable versus continuous, right?
Yes.
Yes. Okay. Thank you.
Yeah.
Yes, but there is also the general infinitely many players with continuity assumptions. So we put the right topology, and that's already, I think, in Pelek's paper. I'm not sure it needed to be countable. It could be any infinite number.
Yeah.
Okay, thank you.
Yeah. So before diving into the class of games I would like to present today, I want to refer to a question that I think Dietmar mentioned, which was what about subgame perfect epsilon equilibrium? And actually, János, in his talk yesterday, already mentioned that there is a Borel game without subgame perfect epsilon equilibrium. And it was presented in this paper with seven authors. A paper with János, and I wouldn't try to pronounce the Dutch names because I'm sure I will make mistakes. But anyway, this is the spelling. And this is a two-player alternating move game. Each player has two moves. And the move is simply to choose the active player tomorrow. So the game starts with player one as the active player in stage 0. And then in each period, the active player chooses who will be active tomorrow. Will it be himself or herself, or whether it will be the other player? So, and then the outcome, the infinite path, would be an infinite sequence of active players, the identity of the players who is active in every period. And the payoff to each player, the F function, depends on this infinite sequence. So if player one is active from some stage and on, then the outcome is -1 for player one and 2 for player 2. If the active player from some stage and on is player 2, then the payoff is -2 to player 1 and 1 to player 2. And if the players keep on changing activity, who is the active player, infinitely often, then the outcome is 0 to both. So this is the game. Now, the payoffs in this game are not tail measurable because it is very important what happens in the first period. And then this game does not have an epsilon equilibrium. Okay. And why is that? Because suppose that the play is such that, the equilibrium play is such that both players keep on switching who is active on the equilibrium path. In that case, the payoff will be 0. But then player 2 would like to be active, because if he is active always, he gets 1. So player 2 will at some point will not pass activity to player one, but rather will keep the activity to himself and get one. But then the payoff to player one will be -2. And then player one will not prefers to be the only active player, because then she gets -1. So that player one will never let player two be the active player. She will be the active player always. So in every subgame in which player one is the active player in the first period, player one will remain always active. So now consider a subgame where player two is the active player in the first period. Now player two knows that if she passes the activity to player one, then she will get 2. Whereas if she keeps the activity for herself, she will get 1. So she will pass the activity to player 2. So player 2 will pass the activity to player 1, and she will get 2. So the only equilibrium possible is that player 1 keeps on being active always, and player 2, if she happens to, in every subgame in which she has the activity, she will pass it to player 1. But then player 1 will not want to be active, because if she is active, she gets -1. Whereas if she keeps on passing the activity to player 2, then activity will switch on, will keep on moving from player 1 to 2 to 1 to 2, and the payoff will be 0. So this is why in that game there is no subgame perfect epsilon equilibrium. So this is a variation of an older game presented by Nicolas Vieille and myself, but essentially this game is a very nice game showing that subgame perfect epsilon equilibrium need not exist when payoffs are non-tail measurable. What happens if payoffs are tail measurable? I don't know. Janos, do you have an idea? No. Okay. So this is an open problem. Okay. So now once we remove the issue of subgame perfect epsilon equilibrium, we concentrate on epsilon equilibrium. And here I would like to present a known game, the big match, that was presented by Dean Gillette in 1957 and then solved by Blackwell and Ferguson in 1968. So the big match is a 2-player zero-sum game, repeated game, where each player has 2 actions. Player 1, top and bottom, and player 2, left and right. And we have stage payoffs. The stage payoffs, U of the action of player 1 and the action of player 2, appear in this matrix. So if so this is a matching pennies game. Okay, so player 1 wants to match the action of player 2 or the other way around. However, this will not be a repeated matching pennies, but there will be a difference. And this is the difference. So denote by T star the first stage in which player 1 plays B. So in this game, player 1 plays T for some periods, and then at some period, at some stage, player 1 will play B. Maybe never, but at some stage, T star, player 1 plays B. And then the payoff, which is a Borel function of the whole play, is given by if T star is finite, so that if player 1 ever played B, the payoff will be the stage payoff at that stage in which player 1 played B. So if at that stage T star, player 2 play left, then the outcome will be 1. Player 2 will play $1 to player 1. If in that period in which player 1 played B, player 2 plays right, then the outcome will be 0. So the outcome in the whole game, the infinite game, will be that payoff in the terminal stage, T star, when player 1 played B. Now, what happens if player 1 always plays T? In that case, we take the limit, the long run average stage payoff as given by the actions of player 2. Okay, so we calculate the average, the long run average of those zeros and ones that were obtained along the play. Okay. So this is the payoff function of the big match. So that we remember that those entries are terminal. Once they are played, once they are chosen, the game terminates and the payoff is determined in the infinite game. I write here stars. So those two asterisks, those stars, remind us that those entries are terminal. And those entries up here are non-terminal. Okay, as long as they are played, the game keeps on being played. Okay, so this was the game, and Gillette in 1957 said, look, this is a nice game. He said something about what the players can achieve by stationary strategies, but he said, I don't know what the players can do here without stationary strategies. Note that this payoff function, f, is not tail measurable, because it depends on, it is affected by what happens in the first stages. For example, if in the first stage the players play bottom left, and afterwards they play top left, then the payoff is 1. Because once the player 1 plays bottom, the game terminates. But if we change the action profile in the first period to top left, then the outcome is 0. Because the long run average of zeros is 0. So this payoff function is not tail measurable. So if you think about, we want to solve the open problem, repeated games without tail measurable payoffs. Let's think about the simplest game that we can that do not have tail measurable payoffs. So we have 2 players, yes. We have 2 actions to each player, yes. 2 of the entries are terminal, are absorbing, right? Once we play them, the game terminates. And only 2 entries are interesting. Only though in those 2 entries, the game can evolve in an interesting way. So this is a very simple class of games. So this is why we started working about this class of games, the big match games. Okay, so let's see this game, the big match, with this payoff function f, which is the limit of the average of the long run average payoffs. If player 1 always plays top, what is the value of this game? By the way, why do we know that the value exists? Okay. Okay, so a question. Does the value of this game exist? You can also write in the chat. I do see the chat. I have 2 screens in front of me.
Well, it's zero sum, right? Or constant sum.
Yes, it is a zero sum game. And so indeed by Martin, 98. The talk of Ron yesterday. This is a Blackwell game, 2 players, zero sum, and therefore finitely many actions, and therefore the value exists. So there is no issue about existence of the value as of 1998. Okay, in 1957, it was still not known. But in 1998, we know that the value exists. Okay. So what is
You
this?
know, you know that the value exists even before, right?
Yes, we will get to that. But at present, what we know, right, in this summer school is only the results that we heard in those 3 days, and Martin is the earlier result that allows us to deduce the existence of the value in this game. But indeed, as I said, in 1968, Blackwell and Ferguson solved this specific game. And afterwards, of course, we have additional results. Eilon Solan extended it, and then Abraham Neyman, together with Jean-François Mertens, extended it to any 2 players zero-sum stochastic game. So we have existence results, but again, what we heard in this summer school is Martin 1998. So player 2, she can guarantee 1/2 very easily. Suppose that player 2 in every period plays half-half, half left, half right. I claim that by playing this strategy, player 2 guarantees 1/2. Why? Because if player 1 ever plays B, then with probability 1/2, the payoff will be 1, and with probability 1/2, the payoff will be 0, so that the expected payoff will be half. Whereas if player 1 always plays top, then the payoff will be the long-run average payoff. But if player 2 plays half-half, then by the law of large numbers, the long-run average payoff will converge to 1/2. So that this stationary strategy guarantees an outcome of 1/2, whether player 1 ever plays B or whether she always plays T. So great, so we know that player 2 can guarantee 1/2. What about player 1? So I claim that that for every strategy of player 2, player 1 has a response that ensures that the payoff is at least 1/2. Those two together ensure that the value is 1/2. Those two claims. So why is this? Why can player 1 always respond by a strategy that guarantees 1/2? So take some strategy of player 2. And suppose that in some period, T, player 2, she plays left with probability YT and Y and R with probability 1 minus YT. Now, if YT is at least 1/2, then player 1 will play B in that period and will ensure an expected payoff of at least 1/2, right? Because YT is larger than 1/2. So if whenever YT is larger than half, player 1 plays bottom and guarantees expected payoff of 1/2. So in that case, player 1 plays B, and if YT is smaller than 1/2, then player 1 plays top. In that case, if YT is always smaller than 1/2, then 1 minus YT is always larger than 1/2. Therefore, in any stage in which player 1 plays T, the expected payoff is at least 1/2. And then by the law of large number, the long run average is at least 1/2. So in both cases, whatever happens, this response of player 1 guarantees a payoff of at least 1/2 to player 1. Any questions? Okay, so So we know that the value of this game is 1/2. But then it is interesting to see that player 1 cannot guarantee 1/2. Player 1 does not have a strategy that guarantees 1/2 against any strategy of player 2. That is, for every strategy of player 1, player 2 has a response that lowers player 1's payoff to below 1/2. Okay, and what is that? So suppose that the strategy of player 1 is to always play T. So against this stationary strategy, the response of player 2 will be always play L. In that case, the outcome is 0 in every period, and the long run average of zeros is 0. So the outcome will be 0. So a strategy of player 1 that always play T cannot be good. It is a bad strategy because player 2 has a response that lowers the payoff to 0. Otherwise, if the strategy of player 1 is not to always play top, it means that there is some finite sequence of actions of player 2 such that the play of player 1 will be top in the first T stages, 0, 1, 2, up to T minus 1. And then in stage T, player 1 will play bottom with positive probability. Okay, so this is the complementary case to always playing T. Okay, if a strategy does not always play T, it means that after some history, it plays B with positive probability. So we take that shortest history after which it plays B with positive probability, and we call that shortest history A to 0 up A to T minus 1. And then suppose that the strategy of player 1 satisfies this property, then what will be the response of player 2? Player 2 will play this sequence of strategies in the first T stages, and then in stage T, she will play right, because in stage T, she knows that player 1 is going to play B with positive probability, so she will play right. And afterwards, if the game was not terminated, that is, if player 1 did not play B, then she will play half-half afterwards. So what is the expected payoff? The first T stages does not affect the long run payoff. In stage T, there is a positive probability of being absorbed to 0. And afterwards, the payoff will be half. So overall, the expected payoff is strictly below half. So as we see, player 1 does not have a strategy that guarantees 1/2. Nevertheless, the value is 1/2. This means that player 1 has a strategy that guarantees 1 minus epsilon for every epsilon positive. And indeed, this is the result of Blackberry and Ferguson in 1968. And they proved that for every integer m positive, player 1 has a strategy that guarantees an expected payoff of at least m divided by 2m plus 1. And the strategy of player 1, it is written here, it is very simple. So player 1 counts the number of times until stage T in which player 2 played left, this is LT, and the number of stages before stage T in which player 2 played right. So this is R of T. And then we calculate the difference, RT minus LT. So this difference is known to the players at the beginning of stage T. And then at stage T, player 1 plays B with probability which is 1 over m plus k2 plus 1 squared. And hocus pocus, this strategy does the trick. it guarantees m over 2m plus 1. So the proof is not difficult. It is by induction anyway, it is by induction of T. Anyway, you can read the original paper by Blackberry and Ferguson. It's a very nice proof. What is the intuition behind this strategy? Suppose that suppose that player 2 plays left often. He plays left more than he plays right. In that case, LT is larger than RT, so that the difference is negative. Now, if player 2 plays left often, then player 1 would like to play B, so that she gets this one, which means that she would like to increase the probability by which she plays B. And indeed, if LT is larger than RT, then KT is negative, it is small, and then M, this difference is small, and so we divide by something which is small, so it becomes a high number. So the smaller KT, the higher the probability to play B. Okay. So this is the intuition behind this strategy, but somehow coming up with this strategy and with those numbers, this is something very impressive, I think. Okay, so this is the big match, the zero-sum big match. Okay, by the way, what is the time? I know. Okay, I don't know. I lost it. Okay, so
60 minutes. 60 minutes.
60 minutes. Good. So so this was the big match, and now I would like to take a variation of the big match, where here instead of payoff 1, it is written C. Okay. So here the value, this is a similar game, and one can show the same as Blackberry and Ferguson, that the value is C over 1 plus C. The intuition is that suppose that player 2 plays the stationary strategy C over 1 plus C. This probability, she plays L, and the probability 1 over 1 plus C, she plays right. In that case, the expected payoff, the expected stage payoff is C over 1 plus C, whether player 1 plays bottom or whether player 1 plays top. So the expected payoff is C over 1 plus C, and therefore player 2 can guarantee C over 1 plus C. And similarly to what we've seen before, for every strategy of player 2, player 1 has a response that lowers, that guarantees at least C over 1 plus C. Okay, so we will need this game in the future. And now to non-zero-sum games. Okay, to zero-sum games, Blackwell and Ferguson solved the big match. And then when we have more complicated games, stochastic games, Mertens and Neyman in 1981 proved the existence of the value. So the interesting thing is what happens when the game is non-zero-sum. So we are going to consider a non-zero-sum version of the big match, where we make only one change in the payoff function, and we will see it now. So again, we denote by T star the first stage in which player 1 plays B. If T star is finite, if player 1 plays B at some point, then the outcome is either 1-0 or 0-1, depending on the action of player 2 at that stage, at stage T star. Okay, so the payoff is either 1-0 or 0-1. The question is what happens when player 1 plays T or top always. in that case, the payoff function is no longer the limit of the averages of stage payoffs, but it is some function of the whole play of player 2. So we have a function u, which is a function from the sequence, the infinite sequence of actions of player 2, left, right, to the power infinity, okay, to R2. And then the payoff will be the u function that depends only on the actions of player 2. Because player 1, she played always top. So there is nothing, her actions are rather the same, are constant. So the only thing that changes is the play of player 2. And the payoff depends on those infinite sequence of actions.
I have a question.
Yes.
You are emphasizing now that the input of one of the players is constant, right?
No. So player 1, she chooses top and bottom in every period.
Yes, indeed.
If she ever chooses bottom, then the payoff is either one.
Yeah. Okay, but in the third case, you said in the third case where T star is infinite.
Yeah.
The input of player 1, I guess it is constant.
Yeah, because in that case, it means that player 1 always played the top.
Yes, indeed. But wasn't this already the case 2 slides ago?
Yeah. Yes.
Because there you didn't emphasize it.
That's true. You are absolutely correct. I didn't, and now I do.
Yeah. Why?
Yes, you are absolutely correct. Yeah. Okay, so if this was confusing my emphasis, then forget it. Okay, I apologize. Yeah.
Eilon?
Yes.
Do you assume that the function, that the game is a constant sum game or zero-sum game?
No, I do not. If it is a constant sum game, it is a zero-sum game, and then we have Martin, right? Martin tells us that in such a game, zero-sum, we have a value. Okay. So this function, this u function, is not zero-sum, not constant sum. It is some general function. It will be bounded and Borel measurable and tail measurable, but it will be not zero-sum. Okay? Okay, so this is our game. And the question is whether this game has an epsilon equilibrium for every epsilon. Okay, and as far as I know, when the COVID started, it was still not known. And our theorem is that if U is tail measurable, bounded, and Borel measurable, then the game admits an epsilon equilibrium. Okay. And this is what I would like to show you today. And then I will talk about extensions. Because I guess that everyone see here that this is a very restricted class of games, and we would like to know how far we can go. So I'll tell you that I do not have a counterexample for a game without epsilon equilibria, finitely many actions, finitely many players, Borel measurable payoffs and bounded payoffs, so that the sky is the limit. But the only question is how closer to the sky we can get. I mean, we personally, not we as a humanity in the future. Okay. So let's see what how we can prove that theorem. So what I do from now on is a proof. Let us denote by VI the value of the zero-sum game with payoffs of player I, where player I is the maximizer and the other player is the minimizer. Okay, so this is the max-min value of player I, or the min-max value of player I. This is a zero-sum game, so the min-max value and the max-min value are the same. Okay, so VI, this is an amount that player I can guarantee in the game. And by Martin, we know that it exists. Also, as already mentioned by Galit and Janosch, since the payoff function is U is tail measurable, this VI is independent of the position that we are, provided we've not been absorbed so far. So provided player one only played T in the past, then the min-max value is the same. Is the same as the min-max value in the continuation game is the same as the min-max value in the original game, in the original starting position. Okay, and this is the tail measurability of U. Moreover, as both Galit and Janosch said, and also Ron, I'm not sure whether you mentioned it or not in your talk, for every delta, player I has a subgame perfect delta max-min strategy. So a delta max-min strategy is a strategy that guarantees an expected payoff of the min-max value minus delta. Okay, a subgame perfect such strategy is one that guarantees this expected payoff after every position in all subgames. But of course, in all subgames in which the play has not been terminated yet. So in all subgames in which player one so far only played T. So we have such a max-min strategy, sigma I delta. Okay, so this is what we will need to construct an equilibrium, an epsilon equilibrium in this class of games. So let us make a few simple observations. First, I claim that the min-max value of player one is at least 0. Why is that? Because player one can guarantee 0 by playing bottom. She plays bottom and she gets either 1 or 0. So her min-max value is at least 0. Okay. So this is a first trivial observation. A second trivial observation is that the min-max value of player 2 is at most 1. Why is that? Because player 2, by playing bottom, she ensures that the payoff of player 2 is at most 1. It is either 0 or 1. So player 1 can always ensure that player 2's payoff is at most 1. Okay, so we bounded V1 and V2 from each from some direction. Now let's consider the case where V1 is strictly larger than 1. I claim that this case is easy as well. Why? Suppose that V1 is larger than 1. Well, if player 1 ever plays B, her payoff is at most 1. So here, if her min-max value is strictly larger than 1, it means that she never plays B in an optimal strategy. She always plays T. But if she always plays T, then the max min will depend on, whatever player 2 plays. This implies that U, the function U, must be for player 2. Sorry, here I miss an index 1. So the payoff of player 1 under U is always strictly larger than 1. Okay, the function U for player 1 is strictly higher than 1. Okay, because the min-max value of player 1 is strictly higher than 1, and if player 1 ever plays B, her payoff is at most 1, so that the only way for her to guarantee more than 1 is by always playing T. So the function U1 is strictly higher than 1. So what will be an epsilon equilibrium? An epsilon equilibrium will be player 1 will always play T. In that case, she guarantees that her payoff is higher than 1, and she has no reason to deviate, because by deviating and playing B, she will get at most 1. Now, what about player 2? Player 2 is free to choose whatever she wants, because player 1 will always play T. So player 2 will play that sequence of actions that maximizes her payoff U2 up to epsilon. And that's it. And then she cannot profit more than epsilon by deviating, because she already plays a sequence of actions that maximizes her payoff. Questions about this simple case? Okay, so we handled another simple case, and then the last simple case that we will handle is the case where V1 is equal to 1 and V2 is at most 0. Ron, do you have a question? No. Okay, so suppose that V1, the min-max value of player 1 is 1, the min-max value of player 2 is non-positive. In that case, the players will be rather happy to get 1, 0. Right? Player 1 is happy to get 1 because her min-max value is 1. Player 2 will be happy to get 0 because her min-max value is non-positive. So 0 is above her min-max value. And then what will be an epsilon equilibrium? So player 1 will play 1 minus epsilon, epsilon stationary, and player 2 will play always left. So under this stationary strategy, the game will eventually, player 1 will eventually play bottom, and the payoff will be 1, 0. Can anyone profit by deviating? So player 1 essentially can profit by deviating, because maybe U, the function U of L is very high for player 1. So we should, in that case, we want to ensure that player 1 does not deviate and always play top. But this is easy. Player 2 simply checks whether the game, whether player 1 played B after 1 million periods. Okay, after 1 million periods, player 1 should have played B with high probability. Okay, I mean, take 1 million to be 1 over epsilon squared. So, and then if player 1 did not play B in the first 1 million stages, then player 2 switches to a punishment strategy against player 1 and reduces her payoff to 1. So that by such a threat of punishment, player 2 can ensure that player 1 does not profit by not playing B. Can player 2 profit by deviating to right? Well, such a deviation is immediately detected. She should have played left, always, and she deviates to right. With probability 1 minus epsilon, the game does not terminate, and then she can be punished by the min-max value, which is negative, non-positive, at most 0. And since anyway she gets 0, it means that she cannot profit much by deviating. So such a strategy is an approximate equilibrium, an epsilon equilibrium for a proper epsilon. So those are two simple cases that we could solve. And now,
Eilon, I have a question.
Yes.
The fact that V2 is at most 0, doesn't it mean that in as long as player 1 plays top, the payoff of player 2 must be at most 0.
Yes, I think so, yeah.
So TL and TR always give 0 or less to Mr. 2, right?
Yeah, I guess so.
Okay.
Yeah.
Okay.
I mean, maybe U2 of LLL can be positive, but the rest, yes, indeed, should be 0.
Ah, yeah, there are no stage payoffs. Okay, I forgot that. Okay, sorry. Yeah.
Mm-hmm.
Yeah. Okay, that's what makes it.
Eilon?
Yeah.
For this case, V1 equals 1, V2 is less than or equal to 0. Can't you start with playing BL in the first period for sure? And if it's not played, then moving to punishment?
No. Suppose that the players play BL in the first period, then player 2 is better off deviating to right.
You're right, yes. I forget.
Yeah. So player 1 should hide the stage. No, I want to explain it to the others. That this is why we play 1 minus epsilon epsilon and not bottom left. Okay. So what are the remaining cases? So there are 2 remaining cases that will be interesting, and we divide them according to whether, according to whether the sum of V1 plus V2 is above 1, strictly above 1, or at most 1. Okay. Now, in the first case, that V1 plus V2 is at most 1, then I claim that V1 is necessarily less than 1. Why is that? This is because if the sum of V1 and V2 is at most 1, and V1, we already handled the case that V1 is larger than 1. So we don't have to handle that. So suppose that V1 is equal to 1. If V1 is equal to 1, it means that V2 is non-positive. And we handled this case already. So that in this case, V1 plus V2 is at most 1, we can also assume that V1 is strictly below 1. We will need it, and therefore I emphasize it, that we can assume that V1 is smaller than 1. Okay. So those are the 2 cases that we still need to handle. Let's handle them. So we start with the first case. V1 is strictly less than 1, and V1 plus V2 is at most 1. In that case, the players will be happy to get V1 and 1 minus V1. Okay, player 1 gets at least her min max value. Player 1 gets her min max value, and player 2 gets more than her min max value, at least her min max value, because V2 is smaller than 1 minus V1. So if the outcome will be 1 minus V1, player 2 is happy. Okay. So the players, we will devise an epsilon equilibrium in which the players get V1, 1 minus V1. And for that, we use the original big match of Blackberry and Ferguson, where here I do not stick 1. The payoff here is C, where C is V1 over 1 minus V1. Why do I want to have C equal to V1 over 1 minus V1? This is because I want the value of this game to be equal to V1. So from the point of view of player 1, the original game, where his value is V1, and this game, where the value is V1, is the same. So again, we plug in here C, the payoff C, and now this is a stage payoff. because this is the Blackberry and Ferguson big match where we have stage payoffs. So the stage payoff here is C. We know that the value of this game is C over 1 plus C. I would like the value to be equal to V1, and therefore I have to plug in C, V1 over 1 minus V1. And so that this is well defined, I need V1 to be strictly less than 1. Okay, and therefore I needed this case that V1 is strictly less than 1. It's between 0 and 1. Okay. So now, how can we devise a strategy in which V1, the players get V1 1 minus V1? Well, this is by telling player 2 to play with probability V1 left and with probability 1 minus V1 right. Okay, so player 1 plays a stationary strategy. Player 2 also plays a stationary strategy, 1 minus epsilon epsilon. Now, if the players play this strategy profile, stationary strategy profile, eventually the game terminates because eventually player 1 plays B, and the expected payoff will be V1 1 minus V1. Can the players profit by deviating? So the answer is no. Player 1, oh, yes, but we will see how. What happens with player 1? Player 1, the only way she can deviate in a meaningful way is by always playing top. Because if she ever plays bottom, well, the game terminates and the payoff is V1 minus V1. So the only way she can deviate is by never playing top, by never playing bottom, that is always playing top. But then, as we did before, in stage 1 million, if player 1 did not play bottom yet, then with high probability she deviated, and then player 2 starts punishing player 1 at her min-max level V1. So such a deviation is not profitable. What happens with player 2? So player 2, why should she play V1 minus V1? She's better off playing right more often. So this means that player 1 should monitor the actions of player 2 and should ensure that player 2 roughly plays V1 1 minus V1. Okay, she does a statistical test that checks whether the empirical frequency of actions of player 2 is V1 minus V1. And if this frequency differs by much from V1 minus V1, player 1 starts punishing player 2. Okay? So this is the way to transform the stationary strategy profile into an epsilon equilibrium. Okay? So this technique is standard in stochastic games. And okay, so far I didn't do much. Those are standard tools. The last case is the case that needs new ideas. And this is the case that we will do now. So here, the interesting case is that when the sum of min-max values is more than 1. In that case, the players do not want to end up here in those two payoffs, because the sum of those two payoffs here is 1, and they can do each one by himself, can do V1 and V2, and their sum is more than 1. So essentially, in an equilibrium, player 1 will have to play top, always, on the equilibrium path. Okay, so let's see what we do here. So suppose without loss of generality that the function u has finite range. Okay, since we are talking about an epsilon equilibrium, we can round the payoffs up to the closest epsilon, and we only add small noise. So we do not really affect the fact that the epsilon equilibrium property. And we choose lambda to be a positive number sufficiently small such that 1 plus 2 lambda is still less than V1 plus V2. So delta is much smaller than the difference between V1 plus V2 and 1. And now we choose a subgame perfect delta max-min strategy for player 2. Okay, where delta is this delta. We will need it actually to be even smaller later, but anyway. So we choose a subgame perfect delta max-min strategy. Now, what happens when player 2 plays this strategy? Her payoff is at least V2 minus delta, right? Because this is a max-min strategy. It guarantees V2 minus delta after all positions in which player 1 only played the top. What is the expected payoff of player 1 under when player 1 plays always top and player 2 plays sigma? I claim that this expected payoff is at least V1. Why? Okay, and this is an important issue. Why does this sigma 2, which is good to player 2, is also good to player 1? So let's see why. So sigma 2 guarantees V2 minus delta at every position, right? So let's look at this this game. What is the probability that sigma 2 assigns to R at a given position? I claim that this probability must be at least V2 minus delta. Okay. I claim that the strategy sigma 2 delta, after every history in which player 1 always played top, plays right with probability at least V2 minus delta. Why? Because this strategy guarantees V2 minus delta at this history. In particular, it guarantees V2 minus delta if player 1 plays bottom. But if player 1 plays bottom, what is the payoff of player 2? It is the probability that she plays right. Which means that the probability she plays right should be at least V2 minus delta. Okay. So we know that the probability of right is at least V2 minus delta. So what is the probability of left? Well, the probability of left is at most 1 minus V2 plus delta. Okay? The sum of probabilities is 1. So if this probability, or the probability of right, is at least V2 minus delta, the probability of left is at most V2, it is at most 1 minus V2 plus delta. But we know that V1 plus V2 is larger than 1 plus 2 delta. So 1 minus V2 is smaller than V1, right? So this probability is smaller. No, this is not a good color. It is smaller than V1 minus delta. Agreed? So the probability that player 2 plays left is at most V1 minus delta. So suppose that player 2 plays this strategy, sigma 2 delta. Now player 1 can guarantee, has a response that guarantees the max min, right? His value. Player 1 can guarantee his value against sigma 2 delta. What will happen if player 1 plays B? Well, she will get the probability of left, which is smaller than V1 minus delta. It is smaller than V1. So by playing B against sigma 2 delta, after every history at every position, player 1 gets a low payoff below her min max. So if she always plays top, she gets at least her min max. Okay? So this strategy, this max min strategy of player 2, it guarantees high payoff to player 2 and also to player 1. Okay? And this is the heart of the argument. I mean, we will have additional arguments. But now we have a suggestion for an epsilon equilibrium, right? What is the candidate of an equilibrium? The candidate is player 1 always plays T, player 2 follows sigma 2 delta. And then player 1 cannot profit by deviating, and player 2 gets more than her min max. Is this an epsilon equilibrium, a 2 delta equilibrium, a something equilibrium? This is a question to the audience.
I guess it is, right? Because player 1 cannot gain by deviating, because then it gets less.
That's true. Player 1 cannot gain by deviating.
And player 2 can't either, because if she plays left too often, then she will be punished. So,
so
player 1 will monitor player 2 and then will build the punishment.
So indeed, we must ensure that player 2 plays sigma 2 delta. Sigma 2 delta may involve randomizations. But then the payoff is not a stage payoff. The payoff is a function of the whole play. And maybe the payoff depends crucially on actions of player 2 that are played in a very sparse sequence of times, in stages with 2 to the power k. And the weight of those, the frequency of those stages might be very rare. And therefore it might be difficult to make statistical tests to check whether player 2 follows sigma 2 delta. Okay? I do not say it is not possible. I say I do not know how to do that. If it is possible, I thought about it a little bit. I didn't see whether we can have countably many statistical tests that check whether player 2 follows the strategy or not. Maybe it is possible. I do not know. In any case, the problem is that player 2 may prefer one play path over another play path in the support of his strategy. And maybe we cannot check that statistically. Okay, so we have to refine our construction. Yes, a question?
So sorry, I have a question. Maybe I take you back a little bit. So if you want, you can ignore my question. I'm just puzzled about, you wrote that if player 1 plays T and player 2 plays sigma 2 delta, then the payoff for player 1, the expected payoff for player 1 is at least V1.
Yes.
And I don't see why.
Okay.
This is true.
Okay. So sigma 2 delta plays right with probability at least V2 minus delta in every position. Okay. This means that it plays left with probability at most 1 minus V2 plus delta.
Okay.
Now, because V1 plus V2 is larger than 1, it is larger than 1 plus 2 delta, it follows that this probability is smaller than V1 minus delta.
Okay.
Okay. Suppose that now player 1 plays bottom. What will be her payoff? Her payoff will be the probability that player 2 plays left, which is at most V1 minus delta.
Okay.
Okay, so now we know that player one has a response against sigma 2 delta that guarantees at least V1.
What?
What is the min-max value? The min-max value, or at least V1 minus epsilon. For any epsilon, she has a strategy that guarantees at least V1 minus epsilon. Is that true?
But it's the min-max of player 2.
No, V1. V1 is the min-max of player 1. So player 1 against any strategy of player 2, player 1 has a response that guarantees for her V1.
Okay.
Okay, so against sigma 2 delta, player 1 has a response that guarantees more, at least V1.
Right.
Okay, what is this response? It cannot involve playing back B, because playing B gives her at most V1 minus delta.
Okay.
So it must be always playing T.
Okay, so T is the best response
Yes.
for player 1 to sigma 2 delta.
Exactly. The
Okay,
stationary strategy T is the best response of player 1 against sigma 2 delta. Hence, the payoff is at least V1. And moreover, by deviating to B, at any position, player 1 loses.
Okay, thank you. Thank you.
Okay, but this is still not an equilibrium because player 2, her play here is random, and therefore she might prefer one play path to another play path. Okay, so here we are going now to use okay, also tail-measurable in a moment. So consider now the expected payoff of player, the expected payoff given this candidate that we have, T and sigma 2 delta, given the history at stage T. Okay, so given the play up to stage T, we consider this expectation, this conditional expectation. Now this expectation, this is a random variable, it is a martingale, because an expectation of a function given an increasing filtration, this is a martingale that converges to the function. So we know that the expected payoff of the players, given the information, given the history up to period T, this is a martingale that converges to U1, U2, to the payoff function U. Now we assumed that the function U has a finite range. This means that there is a vector W in R2, there is a payoff vector, which is more than the min-max value to both players, and there is a position P in which player 1 only played T, such that the probability that U1 and U2 are equal to this W, given P, is higher than 1 minus delta. Okay, so at a far enough point in time, there is a history after which we know that we are close to the limit with high probability.
Eilon, a question. Isn't it rather that it's this payoff or better payoffs even, right?
It is this payoff. It is exactly W1 and W2.
Okay, because if I randomize, why couldn't it be 2 or 3 good payoffs for everybody?
You are absolutely correct that maybe in stage 100, you randomize and you still don't know your outcome. But if you go far enough into the future, you know your outcome.
Why? Is this the tail measurability, or why do you know this?
I don't think so. I think this is just measurability, Borel measurability, because we have here the expected payoff, and we know that it converges pointwise and with probability to U, which means that if we go far, suppose that take some W here in the range. So you know that if you go far enough into the future, you know that you are close to W, which means that afterwards, with high probability, the payoff will be W. So this is not tail measurability, I think. I think it's Borel measurability.
Because if you have too often another payoff or too likely another payoff, you will not get the right average anymore. That's the reason.
Yeah.
Okay, now I understand. Thanks.
I think Levy's 0-1 low is very good to look at for this. Yeah.
Okay, so we can use indeed the Levy 0-1 law, the Martingale-Convergence theorem. They are all they will all deliver it.
Is it just the fact that that the Martingale converges almost surely?
I think so. I mean, this is the argument that I wanted to do here, the Martingale convergence theorem. But if Levy 0-1 law is easier to sum, then fine. But the point is that since the payoff function is Borel measurable, then if we look far enough into the future, then we know with high probability what will be the payoff. And so we have a new candidate for an equilibrium, which is, again, player 1 plays T. Now, player 2 follows sigma 2 until the len P, for len P positions, and then essentially, okay, for len P stages, the length of the position P. And afterwards, she forgets past play and she follows sigma 2 delta as if P occurred. Here I use tail measurability. Okay, so at period, once we are at the length of P, we start playing as if P occurred. This means that our payoff will high probability will be W. Agreed?
So no, I'm not sure I follow. So there is some position P.
Yeah.
After which we know that we are close to the target.
Yeah.
But that P might not be realized.
It might not be realized.
We might, maybe a different history is realized.
Yeah.
So we only wait for the length of P.
Yes.
And then we play according to sigma 2 delta as if P occurred.
Exactly, as if P occurred. But since tail measurable, it doesn't really matter, right? I mean, we get the payoff as if P occurred. Okay? So, and therefore the payoff will be with high probability, it will be W. Okay?
Okay.
Is this an epsilon equilibrium?
Same problem as before. Let's continue.
Indeed, the same problem as before. Indeed, with high probability, the payoff will be W. But with low probability, it might be something higher than W, and player 2 is the one who controls the payoff. So she can make the game, she can make the play such that the payoff is strictly higher than W2, and she can win. She can profit. So it is still the same problem. the fact that with high probability we get W2 does not mean that this isn't, that player 2 cannot profit by deviating. So we need one more thing, one more step to transform this strategy into an equilibrium. Right? We would like to ensure that player 2 does not do that. That player 2 does not play in such a way that the payoff will be not W2. And how do we do that? Well, we go back to Galit's talk about regularity. And here we don't need the regularity of the min-max, but just regularity of measures that Eran already mentioned. Okay? So we consider the set of all play paths in which the payoff is W and that they extend P. And we know now this, if the players follow T and sigma 2, and this is not the original sigma 2 delta, but given P. So we condition on P. Then A has, so this set, it has some probability, more than 1 minus delta, but then we can find a closed subset A of this set whose probability is at least 1 minus 2 delta. Okay? So we find a closed subset. On this closed subset, the payoff is exactly W, always. And the measure of this subset is at least 1 minus 2 delta. Since this set is closed, its complement is open. So which means that it is a union, an open set is a union of basic open sets. And here a basic open set is the set that is defined by a position. Everything that extends some position. And now what will be our statistical test? We do not want player 2 to get outside A. Right? We ask the players to play T and sigma 2 delta. Okay, the same strategy as before. We have the same strategy as here. But now, if the play enters the complement of A, then we punish player 2. Now this happens with small probability at most 2 delta. So punishment occurs with probability smaller than 2 delta. But on A, player 2 cannot deviate because the payoff is always W. And this is an epsilon equilibrium. Questions?
Yeah, what about the following strategy? Player 2, okay. I mean, how can player 1 ever punish? I mean, player 1 can the only punishment you can think of is player 1 playing bottom, right? Because that's the only deviation he has.
Yeah.
Right? So then couldn't I, and let's suppose V2 is not 1, it's smaller than 1. Okay. And now I'm player 2 and I'm have the following idea. I take care that I get out of A, and the first time I get out of A, I play right from then on, and then I know player 1 needs to punish me, and then I get a 1.
The punishment is play dependent.
But maybe
yes, but I could detect when I'm first out of A, right? When I first left A.
Oh, you don't switch to a punishment with an action at that very instant moment. You're moving to a punishment that is play dependent. So you wouldn't know when I am punishing you. When I'm switching to bottom.
Because you only do it with small probability.
Yeah, You will decide exactly when, depending on the play of the other.
Okay, but then I always play right, and then?
Yeah, Martin, it can be that U2, if right is low.
No, but if you always play right under this condition that V2 is less than 1, yes.
Then necessarily U2 of RRR is low.
Okay, okay. Yeah.
So yeah, I mean, deviating to always R is not necessarily a good thing. Indeed, player 1 will not play bottom, but if he plays top, maybe your payoff as player 2 is very low.
Okay, so the way player 1 punishes has to be very careful, right? Otherwise, I could, trick him in this simple way that I just.
Yes. The way to punish, essentially, we are in a zero-sum game, so we are back in Martin's 98 paper, and then we do whatever Martin tells us, which is very complicated.
Yes. One comment, just for my understanding, I think I could have followed if I think that epsilon equilibrium you are looking is much less than delta, but sometimes you refer to epsilon equals delta. And then I think there were a few points that I was not sure that I.
So you should think of delta as much smaller than epsilon.
Epsilon much smaller than delta.
No, the other way around.
The other way.
Delta is much smaller than epsilon.
Delta is much smaller. Okay.
Delta is much smaller. So the new idea here. Sorry.
Yes, but delta is much smaller. Then there was some slide that you showed that when player 1 switches to bottom, then he was losing delta, and delta is much smaller. It would be still an epsilon equilibrium, so it wouldn't violate. So there I was confused.
Okay, so maybe I used the epsilon several times. Not, I mean, playing 1 minus epsilon, I should have wrote 1 minus delta, delta. That would have been better. But so I wasn't careful about when I used epsilon.
Okay. So the spirit I understood. I couldn't match all the epsilons and the delta. Okay.
Yeah. So the new thing here that I see is the use of regularity of measures to construct a statistical test. And this is something I don't know. Merale, have you seen it in the past? At least I haven't.
Sorry, Eilon. So
myself, I said no. Yeah, don't.
Okay, so
I don't remember that, and you should explore it a little more, and maybe even just emphasizing that in a separate paper or in that paper, making statistical tests that are based on the regularity.
Mm-hmm.
So sorry, Eilon. So is it also true that what is also new somehow, perhaps it is not new, that your punishment is somehow stochastic? So if I remember, in many cases, we punish something if we see, okay, he did something wrong. But here you don't say that. You say that with high probability, certain probability, you say that it is wrong. He did something wrong, and then you already punish.
Yeah.
So this is not a usual punishment. So this is a stochastic punishment, let me say, but I don't know what the good term for it.
Yeah, in the literature of stochastic games, it is common to make such statistical tests that with some probability they catch you even if you are honest.
Mm-hmm. Okay, thanks.
Okay, so I didn't say that before. This is a joint work with Galit and Janos and Arkady. So, and what else? So open problems. So this class of games is very restricted, as I said. And now we would like to extend this result. So one extension is to drop the tail measurability condition on U. I think that this will be, this is the first, no. Yeah. So the first extension to drop tail measurability, and that will be the first step into really understanding repeated game without tail measurable payoffs, just Borel measurable. I think this is this will be a nice problem. Another extension is what happens when the game is a little bit more complicated than a big match game. Suppose that we have more than 2 by 2, and maybe the entries, we have more absorbing entries, so they are not as before. And then we have some payoff function U, which is from the collection of all non-asterisk entries to the power infinity to R2. Again, this is the class of absorbing games. To those of you who are familiar with the literature on stochastic games, and we would like to say, okay, U is still tail measurable, but the game is more complicated. The underlying one-shot game is more complicated. Do we have an epsilon equilibrium here, still with 2 players?
So Eilon, how is this different from VA? Because of this more general utility function on non-absorbed plays, right?
Yeah, you have more entries, right? More entries.
No. The question is,
how is it different from VA?
Why it's different from VA? Because of the more general functions.
Yeah. So Nicola VA assumed that U is the limit, the lim sup of average payoffs.
Oh, okay.
So this is one case. This is a special case. So the payoff function that Nicola studied is a special case of this more general result.
Special and more general, because in the other sense, it's not only the proof is not only for the lim sup, but it's kind of a uniform also. Uniform and lim sup, so it's a stronger result.
Yeah.
On a more now, my question is, when you go to absorbing game, I think, you know, you for the big match was kind of conditioning on V1 and V2. Yes. And different cases for different V1 ranges of V1 and V2, the individual rational levels. I think probably the first step in order to move to the absorbing state, general absorbing states, will be to try to rethink of your proof and try to see if you could do it without these cases.
Yeah.
One approach to all V1, V2.
You are absolutely correct, and actually we already did it. So, so indeed, you can somehow put the cases together. I mean, still you have several cases, because actually, if we have to compare this result to the literature, I will compare it to the paper by Vries and Teichmann, the PhD of Frank Teichmann in '89, who studied this game, this absorbing game, 2-player, but with the lim sup of average payoffs. He proved the existence of an epsilon equilibrium. And in the Vries Teichmann paper, we have 3 cases, and also in the case of general tail measurable payoffs, we have a little bit more than 3 cases, but we can do that. Okay, so this case was done. And then the next extension was that Eran Shmaya, I think, already mentioned today, would be for, which will be the second extension that I have here, for 2-player non-zero sum stochastic games with finitely many states and actions. And but here still the payoffs are bounded, Borel measurable and tail measurable. This would be the extension of Nicolas Vieille. We have a proof for that. So we have a candidate of a proof. We still have to verify it, but so this is still under maybe. So we may be here. And then again, the question would be whether we can drop measurability altogether. And that's it. So this is what I wanted to show in this talk.
Thank you, Eilon.
Yeah. So if there are no more questions, I will pass the.
I have another question.
Yeah.
But I want to give some space for others to ask questions. But
I have one more question. You know, there is this thing that Bob Simon was obsessed with, right? And I think you mentioned it. You know, stochastic games.
Mm-hmm.
But
yeah.
you know, with this you know, average payoffs or rim sub of averages and more than 4 players, final many states, final many actions. Is there anything new? I mean, do we know more? Only looking at absorbing games or something? Is there more?
So unfortunately not, or at least as far as I know, in stochastic games with many players, we still don't have existence of equilibrium or a counterexample, as Bob Simon tries to find.
Not even with, you know, 325 players or something, nothing.
Yeah, nothing. We do have results on correlated equilibrium, on various types of correlated equilibrium, but not on Nash equilibrium.
Okay. Is there any, I don't know, in the book you're writing, do you put references for this kind of things?
So the book on Borel games, no, but the book, I do write a book on stochastic games, which actually is going to be sent next week to the publisher.
Could I have a draft then?
Of course, it is on my website.
Okay.
Free for use.
Okay, thanks.
Yeah, so in there I do mention, I do give references.
Okay, thanks a lot.
Yeah, sure.
Thanks for organizing this. This was wonderful.
Thank you for the organizers and for all the speakers. Really very clear lectures, very systematic, both the individual lectures and the structure of the work. So really, thank you.
Thank you again.